The answer is B. This signifies a multiple-choice option in a question related to resistance, potentially within an electrical or electronic context. Given the topic resistance cube, it's likely the question involves calculating the equivalent resistance across specific points on a cube constructed of identical resistors. To understand the solution, let's consider the geometry of a cube and the properties of resistors connected in series and parallel. A cube has 12 edges, and if each edge is a resistor with resistance R, the problem involves finding the effective resistance between 2 points on the cube. There are a few common configurations that are typically asked about. One is the resistance between 2 adjacent corners, another is between 2 diagonally opposite corners on the same face, and finally the resistance between 2 diagonally opposite corners of the entire cube. To solve these problems, symmetry arguments and circuit simplification techniques are employed. The most useful simplification technique is the delta Y or star mesh transform and Kirchhoff's laws. In some cases, superposition can be useful, although it's often more complex. One specific method for calculating the equivalent resistance involves injecting current into one node and extracting it from another. Due to symmetry, the current will divide equally among equivalent paths. Let's consider the case where the voltage source is connected to the 2 diagonally opposite corners of the cube. The current entering one corner will divide into 3 equal parts, 1/3 of the current flowing along each of the 3 resistors connected to that corner. At the next set of nodes, the currents will further divide. By tracing the currents and applying Kirchhoff's laws at each node, one can determine the voltage drop across each resistor and hence the total voltage drop between the 2 corners. The equivalent resistance is then the total voltage drop divided by the total current. Now let's talk about calculating resistance between adjacent corners. Again, symmetry arguments are used. The current entering one corner splits equally into 3 branches. At each of the next corners, the current splits again. Calculating the current distribution and applying Kirchhoff's laws again leads to the solution. Another important aspect to consider is how resistors combine in series and parallel. Resistors in series simply add their values. If you have 2 resistors, resistor 1 and resistor 2, in series, then the equivalent resistance is resistor 1 plus resistor 2. For resistors in parallel, the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistances. If you have 2 resistors, resistor 1 and resistor 2 in parallel, then 1 divided by the equivalent resistance equals 1 divided by resistor 1 plus 1 divided by resistor 2. This can be rewritten as the equivalent resistance being equal to the product of resistor 1 and resistor 2 divided by the sum of resistor 1 and resistor 2. The actual value of the equivalent resistance for each of the cube configurations depends on the value of the individual resistors R. The problem usually gives a specific value for R or leaves it as a variable. Remember that the symmetry of the cube is key to simplifying the problem. By exploiting the symmetry, it's possible to reduce the complex network of resistors to a simpler equivalent circuit that can be easily analyzed. The delta Y transformation is a powerful tool for simplifying circuits with complex interconnection topologies. For instance, it converts a delta configuration of 3 resistors into an equivalent Y configuration, and vice versa, allowing for easier circuit analysis by reducing it to series and parallel combinations. The precise steps for calculating the resistance depend on which points are connected, but the principles outlined above remain the same.